Hello, calculus nerds. In this video about volumes, we are going to talk about solid of revolution and washer cross sections, or just washers. On the left side, we have a visual of a solid of revolution. Basically, it's a function that gets revolved over an axis. And then in the right here, we see a washer method where there's a washer cross section in the center. Basically, a donut. So let's take a look at two examples. Here we go. The first one is about this function 2 plus x cosine x. What I like to do is first just break down the problem, like read the wording and try to figure out what it actually is like. So let's assume we don't have this picture in front of us. The question says the region between the graph of f of x and the x-axis, Okay, all right. So we have just this region that's above the x-axis. Over the interval, now that's super important, over the interval -2 to 2, is revolved about the x-axis. In this case, that means that we're going to have a dx. Everything that we're doing has x values in it. And we're generating a solid when we do that. So we're taking an entire function and rotating it over the x-axis 360 degrees. So we could create a solid. And what I'd like you to visualize is making pottery with the wheel. So we have this big chunk of clay and we're letting it rotate 360 degrees over and over again so that it creates this solid. And at the end here, we're going to see that it's a vase. And many of you have seen this shape before. In fact, it's on the front of a booklet for most of the recent years that I created them. All right, so that I broke that down. My first step is I want to just get that function in my calculator so I could graph it. And obviously I have this here for you, but you graph the function that you're working with and you see if you could just understand the question based on that. So step one, we sketch to get our visual here. Now part of that sketch process is first in your calculator to see it if you don't have a visual, and then second to actually sketch it. All right, so I'm going to do, I guess I'll do the same color here. Basically, I'm reflecting this graph over the x-axis. So on the left here, I'm looking at almost a value of 3. At x equals -1, I see it's 1.5-ish. At 0, we have 2 again. 1 is 2.5-ish. And then at 2, we have 1 point some change. All right, now we're only going up to 2 here, so this extra little piece we don't really need. So I'll just do my best to sketch, and really for the artists in the class or anybody watching this is going to be maybe your favorite part of it, is to just sketch and be able to see what's going on here. Now I'm going to do 3 things from this graph now. Number 1, I want to sketch a circle on the far left, and I like to do the solid line on the left part and the dashed line on the right, and then go to the far right of the interval and create a circle there. So obviously you see an ellipse, but it's actually a circle with perspective. And then finally I'm going to do a common cross section. I'm choosing anywhere in the middle of the interval and creating a cross section of that. There we go. Just made that a little bit better. So this is, we don't need this, right? This is extra. Wonderful. Now I could see that every single cross section of this vase is a circle. And if I just add up all those circles like pieces of paper, then I get the actual volume. The next step is to find out what that area function is. So let's see, let me do this. First I'll say the area is equal to pi r squared of every single circle. And that means a of x is equal to pi times f of x squared. Whoa, whoa, whoa. All of a sudden you're like, wait, what happened? All right, let's look at the radius of each of these circles. This common cross section here. The radius of this circle is the function's value. The radius of this circle here is the function's value. The radius of this circle here is the function's value. So we want to represent the radius as a function because it's changing over time. That means that our area function, plugging that in, is pi times 2 plus x cosine x squared. Not the prettiest area function that there is. Every single exercise that we do, we're writing this area function, what that is. All right, step 3. The lower limit is -2, and that's given to us in the problem. The upper limit is 2. Sometimes we're not given that information. We need to identify that based on what quadrant it's in or how functions intersect and things like that. And the last step is to actually create the integral. That means the volume is equal to the integral from a to b of the area function. And that means the volume in this case is the definite integral from -2 to 2 of pi times 2 plus x cosine x squared dx. So we're almost there. Normally, we'll take the antiderivative of this by hand and integrate that until we have an exact answer with pi in it. In this case, we don't actually have the tools to anti-differentiate this in parentheses. And if you ever come across that, you'll generally know if that's the case, if the answer says write it in decimal. But I'm going straight to Math 9 and entering this integral, -2 to 2. You have to be careful with the parentheses. If you're not sure what's what, you could put this pi in front of the integral. You could just kind of pull that out based on the properties. And then you have 2 plus x cosine x quantity squared. You could also square your function like y1. If you had this in your y equals, you could just put alpha f4 and enter y1. And then if you do it correctly, the answer that you get is 52.43 units cubed, whatever those units are. 52.43. Okay, that is a solid of revolution. And once again, all of our work will include this: a sketch, an area function, writing the limits, and an integral. So if you're working a big blank page, you have plenty of space to write all those. Okay, the next example and the last example in this video is an example about a washer method. And you'll know these when you're given two functions, and you'll be given some information about where they intersect or which quadrant and stuff like that. So let's work through the wording first. The region in the first quadrant, pause. Okay, first quadrant, we only care about this space here. All right, let's assume we don't have this picture though. We're thinking just first quadrant. Okay, all right. Enclosed by the y-axis, weird, right? Enclosed by the y-axis, so first it only tells us the y, and the graphs of these two functions. Now that you see this picture, you can see why they have to tell us that it's enclosed by the y-axis. Otherwise, we'd include all this space here. So it's enclosed by the y-axis in these two graphs. If we weren't given this picture, we'd be sketching cosine and sine. First thing, get it in the graphing calculator or sketch it by hand. Then it's revolved about the x-axis. All right, so that's dx to form a solid. Find the volume. All right, so every time you get a question like this, just analyze the wording first. Okay, let's fill in the space. I heard red plus blue is purple, so I'm going to sketch that purple. It's all of this space in here. Now just think with me first, and I have to erase that purple. We're taking that little triangular shape and we're rotating it. First, we're either bringing it up out of your paper, out of the screen, toward your face and around the x-axis, or back behind the coordinate plane and that way. Okay, now let's sketch it in real time. So I want you to take this point at 0, 1 and reflect it to 0, -1 and draw a circle with dashed lines. And then we're going to rotate this, or reflect this point over here down by the way, the value of these two functions at pi over 4 is the same. It's root 2 over 2, or 1 over root 2, based on what we know about trig. And then we have to do one more thing. We have to take this blue curve and sketch the reflection. So it's kind of going straight and then curving down. So if we reflect it, it's kind of going straight and curving up. Oh, I forgot about the red curve. All right, so we'll sketch that. All right, we got a nice red and blue Pac-Man here. And what's going on? All right, we have this space here, but then they meet. But I'm going to sketch that curve anyways. There you go. That's what that would look like. And now if you turn kind of your head sideways, maybe it looks like a dog bowl. Or if you're looking at it normal, some sort of turbine. And then we have to draw a typical cross section. I'm just choosing a random spot in the middle of the whole visual. Well, I think I wanted to do that in red because that's coming from the red curve. And then I'll do the blue one. And now what I want you to see is that that typical cross section that's in the middle is indeed a donut. So if you're looking at the graph on the right side, you don't necessarily see that. You do see an outside part and an inside part, but you don't really see a donut. You'd have to slice it through the middle. All right, now let's actually do the problem, right? The first step was sketching, and we start with the graphing calculator. We finish by hand. We get that full sketch. Notice that I'm kind of not paying attention to these parts of the graph, so that won't show up in my sketch. The second step is thinking about the area. What's the area of this typical cross section? Well, the area is pi times big R squared minus pi times little r squared. Big R is the red radius, and little r is the blue radius. Now be careful not to actually square the entire thing, so it's not, what do I say here? It's not, I'm not even going to write it because it's not correct. Don't do r minus r and square it. Don't do the quantity squared. That means the area function in terms of x is, forgot my pi. Pi times everything. No, I'll just do it separately. Sorry. Okay. The big R is the cosine function. So it's pi cosine x minus pi sine x. That's the blue function. That is officially the area function of every single circle. And it doesn't even matter if it's at 0 or pi over 4, everything is going to work itself out. In fact, at pi over 4, both are 0 anyways. What's happening is it'll be a root 2 minus 2, root 2 over 2 minus a root 2 over 2. The third step, writing the limits, and that is a equals 0 only because it says enclosed by the y-axis and the graphs of the functions. And then the b value is pi over 4. We had to basically figure that out. It's enclosed by those two graphs, so the location at which the two curves meet is pi over 4. Let's set up our integral now. The integral from 0 to pi over 4 of pi cosine squared x minus pi sine squared x dx. Now, it seems like we might not be able to solve this by hand either, but we actually are. Okay, stay tuned. The rest is just wrapping this up. And here it is. The only thing we need to do in this step is to factor out this pi. So I could pull out any constant into the front of an integral. And I have a little identity I want to remind you of. It's not usually in my short-term memory either. That this expression is equal to cosine 2x. It's basically the multiple angle formula. So let's use that pi and then just rewrite the integral. Many times you'll find yourself rewriting an integral just to make it simpler so your brain doesn't have to work too much, you know? So I recommend doing that. Now we have an actual thing that we could take the antiderivative of, thinking about that 2 with the chain rule, and that means that we have a 1/2. Antiderivative of cosine is sine of that something, sine 2x, from 0 to pi over 4. Hey, that's not too bad. We just really needed that formula, you know? And that's equal to, you could hear my pencil tapping. Sorry about that. That's equal to pi times 1/2 of sine. Okay, pi over 4 times 2 is pi over 2. And then we have sine of 0, which is 0. But if we ever have cosine of 0, don't forget that that's 1. Final step here. Wow, thanks for sticking with me. That happens to be pi times, what's sine of pi over 2? Sine of pi over 2, sine of 0 is 0. So then sine goes up, so sine of pi over 2 is 1. 1/2 times 1 minus 0. Aha! We have pi times 1/2, which is pi over 2. Maybe we could have just guessed that. I don't know. All right. This is the work that I'm expecting you to do if you really want to understand and do the calculus. So for the questions that you work through when you're solving washer cross-sections or solids of revolution, you're doing these steps unless, you know, at the very last step you realize you can't take the antiderivative. Then you're using a calculator for that, using Math 9. Okay, well, a little bit longer than I think I would have liked, but that is solid of revolution and the washer cross sections. Thanks for watching.